Yaskawa.
Welcome to the MotionWorks IEC PRO training session covering sequential function chart programming. And I wanted to start off this topic by explaining what the SFC programming language is and when to use it. And then by means of a simple example, I would like to show how to use the MotionWorks programming environment to build and work with some SFC code. So fire up your licensed copy of MotionWorks IEC Professional and you can follow along with me. So first, what is Sequential Function Chart Programming, or SFC? It is a graphical programming language that lends itself very well to high-level programming of a control sequence. It's basically a flowchart that contains different parts of the program and controls the top-level logic of your program. And so using SFC, the steps of an automated process can be very clearly and simply represented in the program itself. And I think an example best illustrates this. You can see over here on the right, we have some SFC code for a traffic light controller. And so once you know that this is a traffic light controller, with SFC you really don't need to get too deep into the code to get an idea of how the program works. What part of the code is running, what state the traffic light is in. Take a minute here. Starting at the top, you can see that it turns the lights out. Then the green light turns on, which turns off the red light. When the green light's done, the yellow light turns on. That's on for a certain amount of time. And then we come down here to the red light. The red light turns on. When the red light's done, the green light turns on again. And you'll probably notice that this program doesn't really show variables or the outputs that are used. And it doesn't really show, for example, this green done, what they call a transition, doesn't really show what exactly that condition is. And that's because SFC just provides the organizational framework or the structure of the program. It's like the skeleton, the top-level logic, as we've been saying. And so each of these, what are in green here, these actions and the transitions represent a page of code, like a kind of like a subroutine, and that is written in whatever programming language you prefer. It could be ladder, function blocks, structured text. And so I hope you'll agree that this SFC code really very simply, easily, intuitively, naturally describes the function of a traffic light. And so now take a second to think about how you would program a traffic light using function blocks or structured text or, heaven forbid, ladder. I'm sure you could do it, and probably just as well, but would it be so easy for a technician to just step up and assess the situation if there's some troubleshooting that has to take place? And would your code be this well organized? I think in many cases the answer is probably not. So this is the power of SFC. So now that we have in IEC PRO all 5 IEC 61131 programming languages, how do you know when to use one and when to use another? And more specifically here is when do you program with SFC? It's going to be advantageous for you to program with SFC when there is a definite sequence for the machine to follow. And of course, this describes many, if not most, machine applications. So think of SFC when you think of your machine operation as having different states of operation. And as an example, look here at this graphic that outlines the various states a machine might have. It's kind of a general machine. For example, it starts from the off, going to stopped, and starting, then ready, goes to a standby mode, and then finally to producing. And so any machine that would follow this type of state diagram would be a good candidate for programming with SFC. And then thirdly, when to use SFC, think about the future. Who might need to work with the code that you're writing? Maybe it's a technician that has to diagnose a problem in the machine, like we mentioned before. There's a failed part of the machine, or etc. Or maybe there's going to be an improvement or upgrade to the machine program. You as the programmer, of course, may be more comfortable and more efficient using some other programming language, such as structured text or ladder. But if someone else has to work with your code, that person will thank you for programming with SFC. So there are lots of rules and definitions with SFC, but instead of me listing all those out for you ahead of time, what I'd like to do is just learn by doing, and we'll go ahead and do an example. And as I go through that example, it will just take some time to explain what the different features and rules, etc. are. And now, just as a disclaimer, this is not an exhaustive SFC programming reference here. It's not a complete class. There's more to learn about SFC programming. The purpose of this e-learning module is just so that those of you who are familiar with motion control programming, but perhaps new to the SFC language, we want you to just see a little bit of how it works and enough to get you started with SFC in the MotionWorks IEC environment and see how SFC can be used to your advantage. So I want to start by opening up a program that I have prepared here called ProELM_SFC. And I'm just going to unzip it there to that folder that I had. And yes to all to overwrite. And I'll just quickly adjust my environment to my liking by putting the toolbars to the top. And this program is simply a continuation of the programs that I've been working with in the beginning part of this MotionWorks IEC PRO e-learning module, which is also just a continuation of the program that we normally would build in the live class here at Yaskawa. And you can see we've got a lot of POUs already in here. It's really not necessary to have these if you're starting from scratch. You can see what I have here for tasks. I have a startup task that initializes my axis ref variables. I have a fast 2 millisecond cyclic task for the program POUs that control motion. And I have another cyclic task that is a slower task, which is running the logic. So this is the status of my project. As I mentioned, there's a fast task, startup task, and a medium task. I'm going to even show here something that I didn't show in the previous section, which is you can change the name of a task to your liking. So I'll just change this name here. I'll right click its properties and change the name to medium. That's a 10 millisecond task. Okay. Here is the SFC code that I'll be building in this example. Just a little preview here. So I want you to just take a few seconds to look at it and see if you can guess what it's doing. The answer is it's just a very simple motion control program. And starting at the top, you can see first the outputs are cleared. Then it waits for an input 3. Then the motor will move forward, while at the same time, this is the parallel branch, an output will blink. After the move is done, an output will turn on, output 3. And there's another condition that will start the reverse move. There will be reverse move with a time delay of 750 milliseconds before the move happens. And when that move is done, we'll go back to the beginning, back to the top, clear the outputs and wait for input 3 again. So this is a very sequential type of application, perfect candidate for SFC. Just here for reference and for clarification in case there's any question about what the move profile and the timing diagram is. I've got the timing diagram up here. Shows how we have a forward move, a reverse move. You have input 3 turning on, which triggers the forward move and triggers the reverse move with a 750 millisecond delay. We've got output 3 turning on between the moves. And then the whole time that that's happening here, we have output 4, which we'll be using to blink on and off. All right, let's do it. So the first step here is to create a POU. So I'm going to go up here to my POUs, logical POU, and right-click Insert Program. And I'll name it SFC_example. arbitrary name. And for the language, I will choose SFC. This is the same as what we already know. Click OK. And so I've inserted the program POU, but now a good practice here is before you forget, go ahead and add that program instance to the appropriate task. In this case, it controls motion, so I would like this to go to the fast task. So we're going to have to insert the program instance to the task. So in my project tree, I'll go down to the fast task and right-click on it, insert program instance. I can type in any name. I'll call it SFC example. And then I can go down here to SFC example and click OK. So the first thing I'll do here is go and open the code page for this SFC example program, and that's this one here, third one down. And now you notice when I have the SFC code page open, if I put my cursor in the middle, I have some new tools that we haven't had before. Create step, insert branch. And so the starting point here in the SFC environment is to create a step transition sequence. Click that. And what that does is creates a step, a transition, and an action with even a feedback loop. And so these are the default names. S indicates the step, A the action, T the transition. And then for both actions and transitions, as you develop the code behind those pages of code will be, let's say, embedded into the POU and organized in the transitions and actions folders. So as you create it, those code pages will appear there. And it's all part of the same POU as far as local variables are concerned. Now, if you remember back to that original program, the preview of what it was going to look like, we did have 5 different steps. So what you can do is if you want to ever add another step, you just click on the code area and just click the Create Step Transition Sequence again, and that will just put more steps here in series. So I'll just create 5 steps. And now the first thing that I want to show is just putting some descriptive names for the steps and actions and transitions. You really don't have to, and I suppose shouldn't even keep the original names. What all you do is just right-click Properties, change the name to something descriptive, and this is something that can be changed at any time. The one thing when you are naming is to not reuse the name. So if you have a step called FWD, don't call the action FWD. There's bits that are implied, almost like variables that are implied based on the name. So you want to use different names for the steps, actions, and transitions. To change the name of a step, right-click Object Properties, and you type in the name. I'm going to call this one Start. You can see it's the initial step. To change the name of an action, you also right-click Object Properties, and just type in the name. I'll call it Clear Outputs. And you can also right-click on the transitions, Object Properties, to change those names as well. But some of these we'll be looking at this a little later, detail versus direct. I'm not going to change the transition names for now. So I'm going to go ahead and change all of the names here according to my plan for this code. So here I've completed my naming down to step number 5, and I'd like to go back to the presentation and talk about, first of all, the initial step. You notice in the properties for the initial step, it's indicated by a double outline. So when the POU executes, it starts at the step that's marked initial step within the properties. Every SFC has to have an initial step, and of course you can only choose one of them to be the initial step. The other important type of step is the jump step. Typically you put a jump toward the bottom, and the jump will be indicated in the SFC by this little kind of hook arrow pointing up. And in the same way, you'll choose jump, and then you type in the name of the step you want to jump to. So on mine here, my initial step is labeled Start, and so I will go to the properties for this final step, which I just want to be a jump step. I'll right-click Object Properties, and I'll choose Jump, and then type in Start. When I click OK, it notices that this feedback path is going to have to be deleted. So I'll hit Change when it asks me for this. And then I can jump, really, you can have jumps as many places as you want. You can jump to any step you want. Now, as far as the parallel path, I could put that in at this time, but what I'm going to do is add the parallel path a little bit later. So don't worry about the parallel path for now. And instead, I want to get right in here to the code behind the first action, which is called Clear Outputs. So when I double click or right click Object Open, it'll prompt me to insert a page of code describing the action. Notice that the type field here is set to action. It's not a program or a function. It's an action within the same program POU. This SFC example POU, we're creating an action. And that action will be placed in this folder called Actions. I'll just have to choose the language I want to program the action in. And in this ELM, I'll be using the ladder diagram pretty much exclusively. It lends itself well to what we're doing here. So I'll choose LD and click OK. And then it can see it creates this action called Clear Outputs and opens it up for me. And so now in here I have the ladder environment, and I can write a short piece of code. Really all I want to do in this step is be sure that all of the outputs are off. And I could do that by building a rung of ladder and individually turning off each bit. But let me show a little technique here, which is really not part of SFC, but a little good tidbit here. I'll go down to my global variables, and I'll see that my outputs are here, bit by bit, or Boolean by Boolean. And I can also see the hardware address. So I want to insert a variable that will be a word, a 16-bit word for all of these outputs, 0 through 15. So I'll insert a variable and follow the naming convention, MO, module 1, digital output, and I'll just call it bank. That will be a word data type. I'll call that all outputs 0 through 15. And then the hardware address is %QW0. Now I can go back to my code page and use that variable along with the move instruction. So I'll pull up my edit wizard, like that one over here on the right. And I'll find the function called move. And I would like to move the value word 0 into that global variable that controls the outputs, MO1 D0 bank, and click OK. And so there that is. That's my code that turns off all of the outputs to 0. And so to summarize here, what I've done is opened up the first action, created a ladder diagram action that put an action into the actions folder, and then I created the code here, which in this case is very short code, using this technique to set all of the outputs in one step. This could also, again, have been done with just simple ladder rungs. So I'll go back to my SFC example main code here. Let me close some of these windows so I can see. The next step was to wait for input 3. If you remember back to the timing diagram, input 3 was what was going to start the forward move. So if you remember back to our code, we were going to put input 3 just attached directly here to the transition between start and move forward. Right-click the properties of the transition and choose Direct Connection. Right-click Object Properties, change it to Direct Connection. That grays out the name of the transition and puts your little familiar connection blue dot. I now have opened up to me the ladder tools, so I can just take a contact left and a left power rail. Now you might notice that this made a contact that's pretty long. If you haven't done this yet, what you can do is go here to Extras, Options, Graphical Editor, Contact Width, and we tend to like a contact width of 15 I'm just going to do that. Doesn't change those that are already there, but if I were to undo this and add it again, it will make it a little bit smaller here for me. So now I'll go ahead and put input 3 on this contact. Got digital input 3, okay. So now we're down to the next step here, which is the forward step. And we have the move forward action. I'll just double click on it. And I'm also going to choose LD, ladder diagram. I guess function block would also work. I'll just stick with LD. You can put function blocks in the LD anyway, ladder diagram. So now you can see that action's also been added. And I'm going to add a move relative. Make some room here. Open my project wizard. And find the PLC Open Plus MC move relative. So now I'm going to very quickly populate this MC move relative function block. And if you are unfamiliar with how to do that, please refer to the MotionWorks IEC PRO Quick Start video. I would highly recommend that you do that because I'm not going to take the time to explain every step. In fact, I'm just going to cut ahead here to it being completed. So I have a few local variables here for distance, velocity, and XLD cell. For distance, I'm putting in 180 degrees, velocity 90 degrees per second. XLD cell is 3,600 degrees per second squared. I have a move done Boolean, a local variable called move done, and that's the variable that I'll be using to trigger the next step in the SFC page. Also, I'm going to put an error ID, just arbitrary name here that it comes up with, just in case I have an error. I'll have a variable for troubleshooting purposes. What's left here is to execute this block. Notice I have left that blank in my program. And what we're going to do is use what's called the step.x bit. There may be other ways to also execute the block, but this is our recommended method. The step.x bit reflects the status of a given step. So if this forward step is active, if we use the forward.x bit, we will then execute this move relative as soon as that step becomes active. And then likewise, when this forward step becomes inactive, we will remove the execute bit, and that will cause move relative to stop executing. So a benefit to this step.x bit is that you can use it throughout your code to logically force different blocks or different coils to the correct status as this step goes from active to inactive. You don't want to necessarily leave a 1 bit on or leave a function block with the execute bit on as the sequential function chart goes from one step to the next. So back in my code, if I want to trigger on the status of the FWD step, I will go to the execute input and I'll just insert this ladder rung and type the name of the step, which is FWD.x. Click OK. So this is it for the move forward action. Going back to the SFC example, I can see that I now have a transition here that I need to create. What I want to do here is when the move forward action, which contains this move relative block, when that move relative is done, I want that to cause the SFC to go to the next step. And I'll be using the move done bit to do that. So like we did before, I'll right click to the properties, choose direct connection, and then add my ladder rung and choose here move done. It's that easy. For the next step, I have the out step, and I want to set an output. Now, I could do this by just making another action that sets an output, but if all you're doing is writing a bit, you can do that directly within the action itself without writing any code. What you'll do is you'll go in here to this action, and at the bottom left, choose variable instead of detail. And that lets you put in the name of any Boolean variable. It's got to be Boolean. And then the status of that variable will reflect the status of that step, along with the qualifier in front of it, which we'll be talking about a little later. So back here to set output, I will right-click on the properties and change that from detail to variable. And then for my name, this is the name of the variable, I will look for output 3, MO1DO3, and click OK. And now you can see that turned it salmon, kind of pinkish color. And what this means here is that when the out step is active, the output 3 here then will be active, and when the out step becomes inactive, basically when we go to another step it'll become inactive, that output will turn back off. So that's exactly what we want without writing any code at all. So moving down the chart here, we're down to the transition 4. And although this transition 4 is, again, just looking for an input 3, we could just copy that over. I want to show the other way of using transitions, which is to create a code page under the transitions folder. And we call this type of transition a detail type transition. And so if I'm going to use a detailed type transition, I'll right click on the transition, change its name to my desired name, and then I'll insert a transition code page which will appear here in the project tree window. So let me do that. I'll right click object properties. I'm going to call this transition input 3. Leave it as a detailed type. Click OK. Double click to open it. It's giving me a transition. I'm going to use ladder again. Click OK. You can see that puts a transition called input 3 in my transitions folder. This will be most applicable, of course, when we have a transition that is a more complex logical situation. But just for simplicity here, I'm going to make a single ladder rung, and I'll look for input 3 as the contact, module 1 digital input 3. And now somewhere in this code page, there has to be an instruction that controls whether this transition will be true or false back here at this transition point. And this is accomplished by setting a bit with the same name as the transition. So if I put in here for this coil input 3, what that means is that it takes the name, this is automatically takes the name of the transition, and then if this coil is written to as true, the transition is true. If the coil is written as a false, transition is false. And so the name of the transition is of critical importance here, as it is the link between the transition code page and the SFC main code page. I'll go to the input 3 code I was working on and change this coil. We'll call it now here input 3. And you can tell it recognizes that name, it grays out everything else. It's looking for this name, input 3. Okay, the final step here is the reverse move in this sequence. And if you remember, we had a 750 millisecond delay before doing the reverse move. And although you could put a timer, a time delay, right into the code, the SFC language has available what they call action qualifiers. The action qualifier is the letter that you see in front of the action. If you right click and look at the object properties for the action, you see in the bottom here the qualifier. I've got NR, SL, DP, SD, DS, and SL. And so I'm going to select D for delay and type in the amount of time delay I would like to have happen before this action. You have to use the IEC 6731 format, so I'll put in T pound 750 MS. That puts in the action qualifier of a 750 millisecond time delay. So again, it's these object properties that will give you the option to use the action qualifier. Now here I've just got a short list of descriptions of each of the action qualifiers. And we used D, which, as it says here, the action becomes active after a certain time. The step is still active and remains active as long as the step is active. Also, we've probably noticed that N, the non-stored, or I think of it as normal, just means that the action is active as long as the step is active. And you can see with the rest of them here, there's ways to set, limit, delay, pulse to just run at one time, and then different combinations here of storing and delaying and timing and limiting time even. And we don't have time to go into the details of each of these, but I just did want to introduce the concept here of action qualifiers because it's a built-in feature of Sequential Function Chart, and it can save you programming time because you don't have to create timers in many cases or one-shot pulses for your actions. And if you do want to find out more about the action qualifiers, remember that we do have a very exhaustive online help here in MotionWorks IEC PRO. You just go to the question mark here, help about IEC 1131, and just type in the word qualifier. And you can see your qualifiers for action and SFC. It gives the same chart with even more description. I'll close that. Now we need to build the action itself for the move reverse. So I'll double click to open that. Again, I'm just going to choose ladder. We have our code page here for move reverse. And so I'll build up this MC move relative by inserting from PLC Open Plus MC move relative. And so we can see here that move reverse is going to be built just like move forward. But for the distance, I will multiply by -1 to get the reverse distance for this move relative. I'll choose the multiply function, attach distance multiplied by -1, which is L real pound, -1.0. You got to use the right format there. And also remember we have the rev.x, which means to execute based on the condition of this step labeled rev. Back to the SFC code, the final transition we have is another move done. And so again, we could just copy this down here as a direct transition. I'll just do another one as a detailed transition so we can see that again. I'll right click the properties. I'll call it done. It's a detail. I'll now open the transition, make an LD page of code. I'll insert a ladder rung. So all I want to know is when the move is done to turn on the bit, this done bit. And that again goes back to the transition name done. So this is a done bit that will tell us when we're done. This done bit is set by move reverse in this code here. The final feature that I want to add is a parallel branch that flashes an output on and off while the motor is away from the starting position. So that's what these parallel lines mean, is it's a parallel branch. This step will be done at the same time as these three other steps. And so the first challenge here is just to create this parallel branch. And so let me demonstrate how to do that. It's really not too bad. All you do is click on the Insert SFC Branch tool, and then you have to draw and click between the two transitions that you want to have the parallel branch. So right here after this input 3, I'll click here. Gives me now this whole step in action. Place that down and then draw down, and I'll need to go over here to the done transition, and that's it. So let me go ahead here and adjust the labels to say in progress and blink. Do object properties, in progress, properties, blink. And now there's lots of ways to make blinking bits in a ladder environment, but the way I'm going to do it is just to take a system variable called PLC sysTick count and take bit 6 from that counting variable, which will be turning on and off at an acceptable rate, and just write that over here to output 4. So I'll open up my blink action. Again, I'm using LD. Put my blink action here in the page. My first instruction here is conversion, D int to word, so I'll go to type convert functions, and I'll go to d-int to dword, and on the left will be the system variable. Let me just show you where that is here. In the global variables, there's a whole system variable, and it's called PLC sysTick count, and it's a d-int data type. So I've got to convert that to a word so that I can pull out bit 6. You can't pull out bits out of an integer, you can only pull them out of a word or a d word. So in here, PLC sysTick count, and I'll just make up a word, call it flicker dword. Now flicker dword is a dword data type, and I can pull the bit 6 out of it in my ladder rung that I'll create below. So I'll create a rung of ladder. This is another technique here. I'll call it flicker dword. I press dot, and it shows me here which bits or bytes or words I can pull out. I just am choosing bit 6 because I just know that that one turns on and off at acceptable rate. So choose bit 6, click OK. And now for some reason it's not showing the bit 6 here. I'm just going to undo this. I guess 15 in this resolution doesn't display the entire text, so I'll go to layout contact with, and I'm just going to change it here to 21 instead of 15. And let me just put that in here again. It makes those a little bit longer, but you can always move those over. So I'll do this again here. We got flicker word dot x6. There we go. And that's going to turn on output 4. So module 1, digital output 4. And that's my blinking bit. So I'm done creating the code. I'm going to go back here and do a make to be sure that this is all saved and compiles properly. Make. And I have 0 errors. So now finally, let's go ahead and run this program and look at it in debug mode and just be sure that this all works. Now, back in my software, this whole time I've been running offline. So I'm going to now connect my controller and turn it on. And we have a lot of details on how to set up your controller and turn it on for the first time and setting the dip switches. That's all in the quick start video. I refer you to the MotionWorks IEC PRO quick start video. But I'll just take you through some of these steps here just out of good practice. I'll go to Internet Explorer, and I'm just going to test that the IP address I'm expecting does connect. Now you may have a crossover cable, in which case you would use 192.168.1.1. However, I'm using the address that's programmed in there, and I know what it is because it's on a sticker on the side of the demo. And it's 192.168.15.21. And so this proves here to me that I do have connection between the computer and controller. Now back to MotionWorks IEC PRO. I'm going to need to send my configuration to this controller. Just prepare it a little bit. So I'll start the configuration. And then I'll just be sure that this IP address in the top right here reflects the IP address that I am using, which in my case is 15.21. But now don't hit connect quite yet. Instead, go up to the online menu, and I'm going to choose controller configuration utilities. And one thing that's a good idea is to take the current controller configuration and program and everything. It's called the archive, and just archive everything that's on the controller so that you can restore this controller in the future should you need to. So I'll just choose that one and hit execute. It's real quick. I'll just save it here to the desktop and click OK. All right, that's done, so I can always go back now. And then the next thing is just to clear out anything that may be in the controller. I'm going to go to controller configuration utilities again. I'm going to go to the second one down, which is restore to factory defaults, and hit execute on that one. I'll click OK. It's also a very quick operation, and I'll restart. So now I know I have a clean controller. There is no boot project running. And I can now feel free to go ahead and connect to this IP address. Once I see the ready light is on the controller, I'll connect. And since I've cleared everything out here, I'll go ahead and send the offline configuration, which is a configuration that you see here with the axes that are part of this project. Now, if your demo setup is different, you could also just use the configuration found in Auto Discovery. I'm just going to send the offline configuration and click OK. Sending the offline configuration has the benefit that the servo pack parameters that are part of this project will be sent to the servo packs. And now finally, just to make these changes permanent, I'll need to hit the file save. And there's something that comes up here, which is the task assignment for our hardware. It looks like I had the Modbus slave running with the original name for the task, which was called task. And if you remember, I changed that name to medium. So it's just prompting me here that I should select a task for this device to run under. I'll select medium, which is what I changed the name to, and click OK. That's going to save everything for me. And finally, it prompts me to cycle power. So I literally must go and cycle power because it's important that the servo packs and the controller both get a power cycle. So that's done. And as expected, there's a communication timeout during the cycle power, so I'll click OK. After this, I'm done with the hardware configuration, so I'm just going to go and close it. Don't need it open anymore. And back here at my program, I'll just one more time do a make. And now I can send this to the controller using the project control dialog button. And hit download. And download. Now, because I do have one of my tasks set to 2 milliseconds, which is also the setting for the Mechatrol link, in this case they call it the system tick frequency, it does give me this warning. That's fine, we can go ahead and say yes every time this comes up. Now that's been downloaded, I can go ahead and do a warm start. Okay, now we're running, and I can close the resource box. Okay, I'm just going to free up a little bit of space here on my screen by removing some of the panels. And now I'll go into debug mode. And right away you can see here with sequential function charts how it turns red, highlighting the step that you're currently on. So right now we're on the start step and it's clearing the outputs. And if you look here at the demo, you can even notice that the outputs are all off. The next transition is input 3. But I do know that I need to turn the servos on first. And what I'm going to do first is even just put the logo straight up on the motor, because I just need the left motor here. I'll turn the servos on. I can see a confirmation for that on the demo itself. And now the sequential function chart is waiting for input 3. So I'll go over here to DI3 and turn that on. And you can see the motor moves. If I leave that input on, you can see we're just moving back and forth between the two different points. Now in my timing diagram, I had expected this input to be just a momentary input on for some short amount of time, so I'll try it this way now. And we can take a look at the sequential function chart. I'll turn on DI3 and turn it back off. You can see it's now at the out position. And the sequential function chart shows very clearly that step. You can also see that DO3 is on. And running in parallel with that, the blinking action is taking place on DO4. If I turn on DI3 again, just momentarily, I don't know if you saw that there was a little delay. So let me just go through that again. Turn on DI3. And I'll turn on DI3 again. So this time through, I just want to take a look at the code behind each of these actions and steps and just verify how that's working. So right now we're clearing the outputs. I'll double click to open that. And you might see how there is a 3 being written to here from every once in a while. The reason for that is right now there's another POU which is writing to outputs 0 and 1, and so that's why we're sometimes seeing the 3 there, those two outputs on. Now I head here to move forward. I'll open that one up and let's do the move forward. Input 3. See there is forward.x. Now you can't see the done bit turn on because it's just a one scan. Let's move forward. Back here now, we can see the blink action. It's working very nicely. That bit 6 is turning on and off, which is driving my output 4. And we can see over here, output 3 really has no code, it's just the output itself. I'll close that. I could force this true or false, but I'll just close it. And then let's do the move reverse and see how that operates. I'll open up move reverse. Slide this over a little bit. And I'll turn on input 3 here. We'll do that again. I'll do the forward again. And I'll do the reverse. I don't know if you could see there was a little delay. Reverse.x turned on and there was a built-in delay before it executed. The only one I didn't look at here was input 3. I guess that's going to reflect what you see here with DI03. Let's just look at that one to show that when I turn on input 3, that does reflect the status of the switch. Let's do that again. And we're going to go back up to starting position. So this concludes the MotionWorks IEC PRO e-learning module. I thank you for your time and attention, and I wish you good luck with SFC, with multitasking, and with the other features and benefits that PRO offers. Please feel free to contact us with any further questions. 1-800-YASKAWA, yaskawa.com, or training@yaskawa.com. And remember to check out our website. We're always making new videos here to try to help you guys out. So thank you once again. Matt Pelletier signing off from Yaskawa America Technical Training Services. Thank you very much.